So if we start to use models to explain how this works, a really important model is the exponential growth model. And so the equation looks like this. It's a little scary, but it's really not that bad. N sub t is going to be the population at any time into the future. N sub O is going to be the initial population. So let's say we start with a population of 10. R is going to be the growth rate, that's that intrinsic growth rate, and T is going to be time. So the only thing that you really don't know in this equation is E. E is going to be E, the mathematical constant. So it's a number. It's just like pi. It's going to be 2.718. It just keeps going like that. So for our purposes, we just think of it as 2.71. And so let's say we want to figure out what's going to happen to the population in year 1. So if we want to figure out, we started at 10, what's going to be the population probably at year 1, we just use this equation. So E is going to be the same. So what's going to be our R value? Our R value will always be 0.5. That's that intrinsic growth rate. What's our T value? Our T value is going to be time. What's our initial population? It's going to be 10. So if I expand that a little bit, we're simply multiplying 1 times 0.5, 1 year times that growth rate. And so that's going to be 10 times 2.71. Again, that's E raised to the 0.5 power. So that's really like taking the square root of 2.71, and so that's 1.64. So if we work that out, that's going to be around 16 rabbits after 1 year. So let me graph that, and let's go to year 2. So same thing. We're going to plug in our value of 0.5, but now our T value is going to be 2. Still have that same initial population, and so now it's going to be 2.71 raised to the 1 power. So what's that? That's simply 2.71. So if we work this out, now we're going to have 27 rabbits in that next year. You can see the population is increasing. We're starting to see that exponential growth. Let's go for year 3. So if we figure out year 3, again, our intrinsic growth rate is still 0.5. 3 is going to be the year we're at. Still have that same initial. And so this is going to be 2.71 raised to the 1.5 power. You'd probably need a calculator to do this. We now get 44.6, or let's say 45 rabbits. So if we graph it, you can see that the population is increasing like that. We have what's called a J-shaped curve, and it's going to increase rapidly over time. The whole world would be filled with rabbits if we keep following this model. And so we know that's not what occurs. And so not only intrinsic growth rate is important, but K, that carrying capacity. So if you're given a problem like this, could you graph what's going to happen over time? If K is 70, well, you're going to get something that looks like this. It's going to be J for a while, but it's eventually going to curve off, and we're going to have an S-shaped curve. This is a logistic growth model. There's also a mathematical model we won't work through. I'll put a link to another video where I do that down below. And so scientists, now that they have models, they can start to apply that to nature. So what we've found is that species kind of fall into one of two camps. We have what are called K-selected species. Those are going to be species that their population increases, and then it'll eventually hit a carrying capacity and it stays there. What are some characteristics of species like that? They're going to give a lot of parental care to their offspring. They're just going to have a few offspring. And so the whooping crane would be an example of that. Humans are an example of that. We don't just go up and down in our population. R-selected are going to do that. So an Arctic hare is an example of that. A famous study was looking at the pelts that were collected by the Hudson Bay Company, and they found from 1850 to 1930 that the population of Arctic hare just went up and down and up and down. And so hares are going to be groups of individuals that have lots of offspring, they don't get tons of parental care, and their population is going to increase, and then it'll crash. So we have this boom and bust cycle. Now what's interesting is that there's another species, and so the Arctic hare are fed on by the Canada lynx. And if we look at their population goes through a boom and bust as well. We have what's called a predator-prey relationship, where as the Arctic hare population increases, then we can have more lynx feeding on it. But as they crash, then the lynx are going to crash as well.